SwayamPrabha. Digital India. Educated India.
Hello, welcome to this lecture on biomathematics. In this lecture, we will continue discussing some more applications of differentiation and how we can learn whatever we learned so far, how we can use the things that we learned so far to sketch some of the functions, to plot some functions using pen and paper, using hand. Like how do we sketch some functions from the knowledge we gained so far? The knowledge of using the things that we learned from calculus so far, we will discuss how to plot some functions. Before that, we will discuss some of the applications of derivatives. So, we discuss some applications, we will discuss more biological examples, some more examples in biology, and then we will go ahead. So, the lecture is again name is differentiation and its applications, and the simplest. So, as you know, we have been discussing discussing derivative, the idea of differentiation and as a part of the calculus. And when you say derivative, one of the thing that will be very useful is to know that force is a derivative of energy. So, let us have a look at the slide here. The title of the slide is force as a derivative of energy. So, now when I say force is a derivative of energy, let us consider a spring like protein. So, a protein that can be stretched a bit. So, if you draw here, you have a spring like protein, a protein that something like which can be stretched. So, you can apply some force on it and then stretch it. So, you have this energy. So, we know that the energy of such stretching energy is k x square, half k x square. This is the energy. We know that the energy of a spring or anything that like a spring, anything stretching energy, the elastic energy for stretching is half k x square. So, that is what written here, E is equal to half k x square. Now, if you know this energy, finding the derivative of this dE by dx with a minus sign will give you force in this case. So, let us calculate the dE by dx of half k x square. So, what is shown here is as a plot of half k x square. So, this is basically this is not exactly half k x square, it is half k into x minus 3 whole square, something we discussed in the last class, half k into x minus 3 whole square. We discussed this function in the last class, and this is what is plotted here, and that means it has a minimum at x equal to 3 and so on. So, both this function k x square and k into x minus 3 whole square, if you find the derivative, you will get some function which looks like k times x. So, let us see first what is the derivative of half k x square. So, let us look at E is equal to half k x square, dE by dx is half times d by dx. Half is a constant, so you can take it outside. K is also a constant, so you can also take k as also outside. So, it is basically k by 2 into d by dx of x square. So, it is basically d by dx of x square is 2x. So, k by 2. So, you know that x power n has n x power n minus 1. So, it is basically k by 2 into 2x, which is kx. So, this is the derivative half k x square, which is kx. Now, if you add a minus sign here, you can add a minus sign here, everywhere a minus sign. So, the answer also will have a minus sign. So, that is minus kx. So, we all know that the force to pull a spring is minus kx. The kx, the minus sign only indicates the slope or the direction of the force which is towards the center. So, the restoring force, so minus sign. So, essentially half is equal to f half kx square as a derivative of this potential energy is force. So, this is one thing where you always would need in biology to calculate forces, because different kinds of potential energies, like there is electrostatic potential, there is elastic potential. So, all these potential energies, if you find the derivative of these energies, you will find basically forces. So, and forces is a useful thing which you can measure and which is important. So, any two charge, for example, when they move together, let us say you have a positive charge and a negative charge. When they attract each other, one charge is attracting the other one and pulling them together, the force with which they attract is basically the derivative of energy. So, the force and energy are derivatives, which are very useful quantities which we might need to compute. So, this is one application of differentiation. So, again, how do we use this idea of force in biology? So, there are very interesting experiments, especially like in this era where we have very fancy tools to do experiments on single molecules even, and using those experiments where we can measure force and gather some information about some biomolecules. So, we will discuss now an example where you apply force on a biomolecule and you measure something related to force and gather some information about the biomolecules, about energy and force and so on. So, let us look at the next slide. So, what you see on the left side is a schematic cartoon like diagram where you have a DNA. So, this is a sketch for a DNA, the red one. So, you have DNA which all this A's, GTC, all this base pairs connected here, and this is base pairing broken here. So, this is one strand and this is the another strand. And imagine that one strand of the DNA is connected to a fixed glass plate or something. This is like a glass plate. So, you can attach one end of the DNA to a glass plate using some chemical, using various, there are different ways using which you can attach an end of a DNA to a glass plate, and you can apply a force at the other end of the DNA. One of the strand you can hold and apply a force. There are different mechanisms by which you can apply a force. They are called magnetic tweezers or optical tweezers, or even AFM can apply some force on the DNA. So, there are different equipments available now using which you can apply force. So, imagine such an experimental assay, an experimental setup where one end of the DNA strand is held at a fixed position attached to a glass plate and the other end is being pulled. So, we attach one end and the other end is pulled, so that the DNA is zipping apart, unzipping. So, these are called DNA unzipping experiments. So, you might know that if you increase the temperature, the DNA will melt, the base pairs will break, and then they will unzip and become two strands. You can separate those two strands. Instead of temperature, you can use force, which is another thermodynamic variable, just like temperature, force is a variable, and you can apply a force and you can measure the distance. So, in thermodynamics, there is a quantity called free energy, which most of you are familiar. So, there is a quantity called Gibbs free energy, which is often denoted by G. This Gibbs free energy is a function of temperature and it is a function of the force or the pressure. So, here is the force. So, you can measure the Gibbs free energy and the value of the Gibbs free energy depends on how much temperature, what is the temperature of the system and what is the force you apply. So, in this case, the case of unzipping, applying a force, you fix the temperature to, let us say, 300 Kelvin or a 310 Kelvin, whatever you wish. You fix the temperature as a fixed constant, then you vary the force, and then you can get the Gibbs free energy, G of F. So, once you know the Gibbs free energy, the relation between the Gibbs free, so you can apply a force and measure this distance. So, this d is the distance from one end of the strand to the other end where you are applying a force. So, this distance is d. So, if we know the Gibbs free energy, we can predict the distance versus force relation by this particular relation. So, what I wanted to say here is that the free energy and the force and distance are related in such a way that through a derivative. So, what is written here is that if you know the g, the distance d is given by dg by df, given that the temperature is a constant. So, here the d is the distance, as you see in this picture here, d is the distance, this is the distance d, and the more the force, the more the distance in this case. But using this relation, one can get we can make a plot versus the force versus distance. You can make a force versus distance curve. So, let us say it could look something like this, we do not know, depending on the experimental system, the plot could look in different ways, but this plot can convey a lot of information. For example, let us say about the strength, some of the base pair is very strong, like then you need more force to unzip it. So, some of them are like not so strong, then they can come off very easily. So, depending on the nature of base pairing, depending on their GC or AT, you would have different forces to unzip them. Let us say all of them are AT, the force could be different, and all of them are GC, the force could be different. So, one could, by just getting the plot versus d versus f, you can imagine that one could get some idea about the content of the DNA, and also one can get some idea about the force needed to unzip it. So, just like melting temperature will give you some information about the DNA base pairing, you can also imagine that this kind of experiments can also give some information about the DNA structure. So, this is some experiment which is used very, it is like a experiment that has been people have been doing this recently, like post 90s and like in 2000s, like last 20 years people have been trying to do this kind of experiments, and they use this kind of relation where free energy is related to the force and distance such a way that the distance is derivative dg by df. So, this is the idea. So, here is another example where you have free energy and the derivative is being used, for using which you can learn something about the system. So, that is the basic thing that I wanted to convey you through this. So, now we will go to the second, the part I was talking about, were using the idea we learned so far, how do we plot some functions. So, let us look at the slide here. So, the theme here is plotting curves, and the question is how the ideas from calculus that we learned so far can help us in plotting functions. So, we want to plot any functions using pen and paper. We want to quickly figure out, if somebody says you x cube minus 3x, or any function like a 2x square minus 23x, or even e power minus x sin x, any of this function, how does this function look like? Without figuring out each point by point, can we schematically plot this function? We can. We do not need to figure out. So far what a computer, or what the way you know it as of now, is that any function, you know, let us say x square you calculate the square for each point, take x equal to 0, calculate square, x equal to 1, calculate square, x equal to 2, calculate square. So, that is the way we used to calculate, but we do not need to calculate for complicated functions. You can easily plot it, you can schematically, you can roughly know how will the function look like by knowing some ideas that we learned so far. And what are the ideas? The ideas we learned last few lectures, for example, we learned about maxima and minima. So, the clue which I wrote here is that we can now figure out locations of maxima and minima of any function. We can know that where is a function as maxima and minima. So, what does it mean to say a function as maxima and minima? Let us think about it. Let us say you have a function, let us look at this plot. Let us say you have some function looks like this. So, this is a maxima, this is a minima. So, whenever there is a maxima and minima, the function is changing from increasing slope to decreasing slope. That is changing its direction, right, just curving. So, you can already find out the places where the function is going to curve. For in other words, it's like some other function, let us say the function which might look like this. Some other function can look like, as we were discussing the free energy, some function can look like this. So, all these functions have minima or maxima, where the function itself is changing its slope from either positive to negative or negative to positive. So, the slope is being changed. So, that is the main points where it changes its direction. So, these points that we can now figure out these points by knowing whether where is maxima and where is minima of any function. It will help us in figuring out the rough shape of the functions. So, I am going to describe a recipe for plotting sketching functions. The recipe is that you have to do 1, 2, 3, 4, 5, 6 steps, like there are like few steps. If you do these steps, if you follow these steps, it's like a protocol in biology. If you follow these steps, very likely that you will end up with some reasonable description of this plot of the sketch of this curve. So, from whatever the idea you learn so far, you can follow this protocol, this recipe, and end up with a sketch of any function, pretty much any function. So, let us see what is the protocol, right. So, let us see here. So, the recipe here is that, let us have a look at the slide. The recipe here is that, so the recipe for sketching f of x, the first point is that evaluate f of x at 3 points, f equal to infinity, f equal to minus infinity, f at x equal to infinity, x equal to minus infinity, and x equal to 0. So, these are the 3 points where they are like kind of extreme points, right. So, if you have any function f of x, the first thing we want to know is that at infinities, like when x equal to plus infinity or x equal to minus infinity or x equal to 0, how does this function, what is the value of this function? If we know that far away the function either should go to 0, far away the function should go to infinity, far away as you go along the x axis, as the x goes to infinity, the function should reach a particular value. So, we have an expectation, where should the function essentially eventually end up at this particular value. So, the first thing in this recipe, in this protocol, is take any function, calculate any function like say x square or x cube, calculate what happens when x equal to infinity or x equal to minus infinity and x equal to 0. This is the step 1. Okay, step 2 is, as seen here, is find out the point where f of x equal to 0. So, find out the point where f of x equal to 0. So, that is this points where, so let us say you have any function. So, this is x and this is f of x or y, and first we find out as we go to infinities, this ends, what is the value of f of x, and then second one we find out for what value of x this f of x will be 0. So, that will give us some idea whether where is the function crossing 0. If the function is, this is 0, and if it is crossing 0 at some particular point, if the value is 0, that means it is touching 0 there, that means it is likely that it might cross 0 there. So, the second thing we do is find out the value at which it will cross 0. So, find out the points where f of x equals 0. And the third thing is calculate the points where the function has maxima and minima. So, any function could have many maxima and many minima. So, as we learned in the last few lectures, by calculating the derivative and equating it to 0, the point where the derivative is 0 is either a maximum or a minimum. So, this is the next thing we want to find out. The third thing we want to find out is for what value of for what value of x the function has derivative equal to 0. So, find derivative equal to 0 and find out what is the value at which this becomes 0. That is the third point. And the fourth point is among you find many minima, and which of this minima, which one is a maximum and which one is a minimum. If the second derivative is less than 0, we know that it is a maximum, and if the second derivative is greater than 0, we learn that it is a minimum. So, the next point is find out which one of it is a maximum and which one of it is a minimum. And the next point is evaluate the function at maxima and minima and make a schematic sketch using the above information. So, here is the recipe, and what we will do now in this lecture is we will take one by one, take an example, and we will follow this protocol, follow this recipe step by step and see what we get. So, thereby we will learn it, you will learn it how to do this. So, let us now take an example. So, the example that I want to study is f of x equal to x cube minus 3 x. So, this is the example which I want to use today, basically to teach you how to plot this function. And the first instruction, the first in the protocol, the first instruction in the recipe is that evaluate f of x at 3 points, f equal to infinity, x equal to infinity, x equal to minus infinity, x equal to 0. At these 3 points you want to evaluate f of x. So, let us start this. So, the function we have is x cube minus 3 x, this is our f of x. This is our function, and what we want to find out is that first we want to find out f at x equal to infinity. This is the first thing we want to find out. So, that means you have to substitute for x equal to infinity. So, infinity cube minus 3 times infinity. So, you know that anything that infinity cubes will be like infinity. So, in the limit x going to infinity, where the x is very large, this is very likely that f of infinity will go to infinity. So, as the x tends to infinity, this function likely to go to infinity. So, the next point we want to find out is at x equal to minus infinity, what will be the value. So, now next one we find out f at x equal to minus infinity. So, here look at this function, if you put minus infinity here, minus infinity cube, infinity, so 3 times multiplying. So, there will be a minus sign here. So, this term which is dominating term, this is the dominating term. You all know that we can guess that when x is very large, x cube is the dominating term. Like for example, if x is 10, x cube is 1000 and x is just 10. So, 1000 is much larger than 10. So, whatever be the sign of this 1000, that will be the dominating sign. So, x cube is the dominating term, and you can see, imagine that as x goes to minus infinity, this function will goes to minus infinity, because this is how this cubic function goes. So, as x goes to infinity, this will go to minus infinity. Now, the next one is what happens when f of x equal to 0. So, our function, as you know, let me write this function here again. The function is x cube minus 3 x, this is the function. So, at x equal to 0, you put 0 here, 0 here. So, this is 0 minus 3 into 0, 0. So, f of x equal to 0 implies this is equal to 0 itself. So, the function is f of x equal to 0 is 0. So, the function is 0 there. So, what we saw now is that at 3 points, at plus infinity the function is infinity, at minus infinity the function is minus infinity, at x equal to 0 the function is 0. So, this is the summary. So, look at this, the summary is that x equal to infinity the function is infinity, f at x going to minus infinity the function is minus infinity, and as x goes to 0 the function goes to 0. So, these are the 3 limiting values. This is 3 points where for extreme values of x infinity and minus infinity you have this function going to infinity and minus infinity, and x equal to 0 is 0. So, we know these 3 values. So, what does this help? Knowing this, how does this help us? So, let us see how does this help us. So, let us plot. So, let us, this is x axis and this is f of x. Now, what we know? We know one thing, that when x is 0, so this is x equal to 0. So, let us call it x equal to 0. So, we know that at x equal to 0 the function is 0. So, it has, the function has to go through this particular value. So, we learn that f is equal to infinity is infinity, f is equal to minus infinity is minus infinity, f is 0 is 0. So, we know that f is 0 is 0, and as this goes to a larger value of x, as f goes to infinity, as x goes larger and larger, the function should go to infinity. So, as x increases, the function should go to infinity. This is the way function, this is the only way the function can go to infinity. Like some way, as the x increases, the function also should increase, then only it can go to infinity. And you know that at 0 it has to be 0. So, from here it has to go and increase somehow, and f equal to minus infinity, as the x decreases to goes to this way, the function has to go to minus infinity. This is what it says. So, this says that as x goes to minus infinity, the function should also go to minus infinity. So, the minus infinity is here somewhere at the bottom. So, the function should, as x goes, the function will go to minus infinity. So, the function will go to minus infinity. So, these two edges, these two ends are clear. At plus infinity it has to go to infinity, at minus infinity it has to go to minus infinity, at x equal to 0 it does this 0. So, these 3 things are clear. Now, how is it this in between here, which we do not know, which we will find out. So, but we got some clue already that at 3 ends the function will go to minus infinity, plus infinity, at 0 it is 0. So, it has to go through this point. So, this much is clear. Now, let us look at the next point in the recipe. So, the next point in the recipe is that find out the points where f of x equal to 0. So, find out the points where f of x equal to 0. So, the points where the function is 0. So, that means the points where x cube minus 3x is 0. So, let us see where are the, when is x cube minus 3x is 0. So, x cube minus 3x equal to 0 implies, so there is x and x you can take out. So, you divide throughout by x. So, you get x square minus 3 equal to 0. I can divide this term and this term by x. So, you will get that x square minus 3 equal to 0. This implies that x square is equal to 3, because I can take this 3 this side. This implies that x is plus or minus square root of 3. So, when x is plus or minus square root of 3, the function is 0. So, square root of 3 is what? Square root of 4 is 2. So, square root of 3 is just below 2, so like 1.7 something. So, when x is just below 2, just you will have this function f of x reaching 0. So, let us look in this plot. So, here you have x equal to 0, here you have x equal to 1, here you have x equal to 2, here you have x equal to 3, and so on and so forth, and here x equal to minus 1, x equal to minus 2, x equal to minus 3, and so on and so forth. So, what we found is that when x is about square root of 3, which is about 1.7, which is very close to 2, somewhere here the function should reach 0. So, at least plus or minus square root of 3, at plus square root of 3 and minus square root of 3, the function should have hit 0. The function should pass through these points. This must be understood. Okay. So, and the next one we want to find out is that, so now let us look at what is the next thing in the recipe. So, the next thing in the recipe is that find out, so this is the what we found, that x equal to 3 points. So, even at x equal to 0, there is, sorry, I forgot to say one thing, that even at x equal to 0, if you have put x equal to 0, you still get the function 0. So, even 3 points. So, if you look at this point, this point and this point, these are the 3 points where the function will reach to 0. So, these are the 3 points where the function is 0, and the next one is, the next thing in the recipe is that calculate the points where the function has maxima and minima. So, how do we find out, what does it mean? That is, when if you calculate df by dx, that is the derivative, and equate that to 0, wherever this derivative is 0, those points are the points where you have either maxima or minima. This is one thing which we learned before. You calculate the derivative, equate that to 0, the points where the derivative is 0, you have maxima and minima. So, now what is df by dx? So, let us go back and learn once more what is df by dx. So, as we learned, x is equal to x cube minus 3x, sorry f of x. This is f of x equal to x cube minus 3x. Derivative, which is df by dx, is equal to what is the derivative of this function? So, derivative of x cube is 3 x square. This is what we learned. X power n has derivative n x power n minus 1 minus the derivative of 3x is 3. So, the derivative of this function is 3 x square minus 3, and we want to find out where is 3 x square minus 3 equal to 0. The point, the value of x at which this derivative is 0. What we want to find out? We want to find out the points of the values of x where 3 x square minus 3 is 0. What does this mean? So, I can take this 3 this side. So, I want, so this would imply, this would give that, this means that 3 x square equal to 3. So, if I can take this 3 this side, what this implies is that 3 x square equal to 3. So, I can cut this 3 and 3, which is means that x square equal to 1. When x square equal to 1, 3 x square is 3, which implies that x is plus or minus square root of 1, which is 1 itself. So, when x is plus or minus 1, you have x square 1 and 3 x square is 3 and 3 x square minus 3 is 0. That means, when x is equal to plus 1 or minus 1, the derivative df by dx is 0. So, we learn that at x equal to plus 1 or and minus 1, you have an extremum, you have extrema, you have either maximum or a minimum. So, there are two extrema, we do not know if it is maxima or minima yet, but we know that this at x equal to plus 1 or minus 1, there is either a maxima or a minima. So, that must be found out. So, let us go back to this curve. So, at this point x equal to plus 1 and x equal to minus 1, at this point and this point, we have either a maxima or a minima, but we want to find out whether it is a maxima or a minima. So, that is the next thing in the recipe. So, let us, so what did we find so far? X equal to plus 1, so we have to find out this. So, we found that x equal to plus 1 and minus 1, we have maxima or minima. Now, how do we find out whether it is a maxima or minima? So, the way to find out is that find out which one is a maxima, which one is a maximum and which one is a minimum. So, we have two extremas here at +1 and -1. Now, we want to find out which of this is a maximum, whether it is a maximum, if it is a maximum, or which one is a minimum. Now, the way to find out is that calculate the second derivative d square f by dx square, and if it is greater than 0, it is a minimum. If the second derivative is less than 0, it is a maximum. So, let us, this is what is written here. If d square f by dx square is less than 0, it is a maximum, and it is a minimum if d square f by dx square is greater than 0. So, what we want to find out is d square f by dx square. So, let us have a look at it. So, we have a function is x cube minus 3x square 3x, and we found that this is our f, and we found that df by dx is 3x square minus 3, and d square f by dx square, another derivative of this. So, what is the derivative of 3x square? X square has a derivative 2x. So, 2 into 3 is 6. So, this is 6x, and derivative of 3 is 0. So, the second derivative is 6x. So, that is what we have written here. The d square f by dx square, the second derivative of this function is 6x, and we found that when x equal to +1, it is something, either a maxima or a minima, and x equal to -1, it is also a maxima or minima. So, now let us substitute x is equal to +1 or -1 here. So, what we want? We know that at x equal to +1, it is either a maxima or a minima. So, let us substitute x equal to +1. So, we have d square f by dx square equal to 6x is equal to 6 into 1. So, we substitute x equal to 1. So, you get 6. So, which is greater than 0. So, at x equal to 1, the second derivative, that is 6x, is greater than 0, because at x equal to 1, 6x is 6. So, 6 is greater than 0. So, at x equal to +1, the second derivative is greater than 0. This implies that a minima, it is a minimum. Whenever the second derivative is greater than 0, it has to be a minimum. Now, let us have a look at the next one, which is, so we found that the second derivative d square f by dx square is 6x. At x equal to +1, d square f by dx square equal to 6, which is greater than 0. At x equal to -1, what do we get? D square f by dx square is 6 into -1, x equal to -1, we are putting x equal to -1. So, this is -6, which is less than 0. So, if it is less than 0, this would imply that this is a maximum, here is a maximum. So, here this implies that it is a maximum here. Here, as we learned, when x at x equal to +1, you have a minimum. So, we have a minimum here and a maximum here. So, let us look, this is what we in the slides we show that at x equal to +1, it is a minimum. So, it should be written as a minimum, and there is an error here, it should be written as x equal to +1, it is a minimum, and x equal to -1, it is a maximum. Okay. So, let us look at this plot once more. So, what did we learn? We learned, let us look at this. So, we learned that x equal to +1, it is a minimum. So, here at equal to +1, the function should have a minimum. That means, the function should have something like this. So, we do not know what here it is, here or here or here, where is this minimum, but we only know that it is a minimum at some particular, at any of this point you should have a minimum, and at this particular point you should have a maximum somewhere. It should have a maximum somewhere. We do not know where is it, it is here or here or here. We do not know where is this maximum, but we know that at x equal to minus 1 it should have a maximum, the function should look like this, a curvature like this, and at equal to plus 1 it should have a minimum where the function should look like this. Now, what is the value at which this maximum and minimum should happen? So, we should evaluate the function at x equal to plus 1 and minus 1. So, let us the next recipe, let us go to the next recipe. So, here next one says evaluate the function at maximum and minimum. So, there are again error here, should read as evaluate the function at maximum and minimum. So, I take x equal to plus 1, x cube minus 3 x is minus 2, and so at x equal to minus 1, x cube minus 3 x is plus 2. This you can see. So, how do we see that? So, let us learn how do we see that. So, the function is x cube minus 3 x. So, x equal to plus 1 implies that 1 cube minus 3 into 1, which means 1 minus 3, which is minus 2. So, at x equal to plus 1 the function is minus 2, and x equal to minus 1 the function is minus 1 cube is minus 1, minus 3 into minus 1 is minus 3 into minus 1 is plus 3. So, this is plus 2. So, at x equal to plus 1 it is minus 2 and x equal to minus 1 it is plus 2. So, what does this mean? This mean is that at x equal to plus 1 the function is at minus 2, the minimum is at minus 2. So, this has to be minus 2. So, this has to be minus 2, and x equal to minus 1 this maxima happens at plus 2. So, at plus 2 there is a maxima and a minus 2 there is a minima. So, we know this much thing, we know a lot of things now. We know that, so have a look at this, we know that at the ends it goes like this, and we know that there is a maxima here and there is a minima here, and we know that it should go through 0 here, it should go through a 0 here, it should go through a 0 here. So, if we join all this together smoothly, it should. So, let us join all this together. So, let us draw all this knowledge, let us combine all this knowledge into a nice graph. So, let us combine all this knowledge. So, what do we know? So, let us again draw this axis. So, this is x and this is f of x. So, now we know that at x equal to, so what do we know? We know few things. We know that the points where it is 0 is that at root 3, square root of 3, that is here, somewhere here and somewhere here. So, this is like, let us call it, this is 1. So, let us call this is 1, this is 2, this is 3, and this is 1, 2, 3, and this is plus 1, this is 2 and 3, and this is minus 1, this is minus 1, minus 2, minus 3 and so on. We know that at square root of 3, plus or minus square root of 3, the function is 0. So, somewhere here and somewhere here the function is 0. Here is also a function 0. So, these are the 3 points where the function is 0. And as it goes far away, it should go to infinities. It should go to infinities. And we also know that at x equal to plus 1, there is a minima at minus 2. So, x equal to plus 1, there is a minima at minus 2. So, we know that there is something like this here, something like this here, and we know that there is a maxima here and it should pass through this. So, this it should pass through this 0 and it has to have a maxima and a minima, and then again it should pass through this. This is another point where it should pass through 0. So, it should pass through this and it should go to infinity, and again here as a minima, and then it should pass through this, then it should go to infinity. So, this is some function which has a maxima and a minima, and then it should go to infinities at both the ends. So, the function should look like this: one maxima, one minima, one maximum, one minimum, and at either ends it should go to infinity, and these are the points where it should hit 0. So, knowing this much, we could just join together, and the function will look like this. So, this is how the function looks like. So, there is a maximum, there is a minimum, and it should look like this. So, this is how you schematically plot a function. So, this is one example where you schematically plot a function. Now, we will take one more example and then just discuss how do we schematically plot this function. Now, that we learn this one example, which is x cube minus 3x, and the protocol, we have the protocol for plotting it, we should take another example. So, the example I am going to say is a function which is very well known in various fields, and this function basically describes the interaction between two atoms. So, this is called Lennard-Jones potential. So, the function looks like this. So, the function which I am going to describe is f of x is a by x power 12 minus b by x power 6. This is the function which we want to plot for some particular value of a and b, and we know that a is some value greater than 0, b is some value greater than 0. This much we know, some numbers, a and b are some numbers, it could be 6, 3, we do not know, any number which is greater than 0. So, this is called a Lennard-Jones potential, and this describes the interaction between two atoms. So, we will quickly go through this protocol and try and plot this function quickly, but you should take it as an assignment yourself and try and plot it yourself, you following the protocol that we described. But let us just quickly go back to the protocol and then see how do we plot it. So, the protocol we say here is this. The first one is evaluate the function at 3 points, at infinity, I did 2 plus infinity minus infinity at 0. So, let us start doing it. So, our function here now is that a by x power 12 minus b by x power 6. This is our function, and if you put x equal to infinity, what happens? So, but now one thing which you should understand, I should tell you, like we should imagine one thing. So, we are plotting this function basically represents the distance between two atoms, so like the interaction of two atoms. So, when you say two atoms, the closest the two atoms can come together is 0. There is nothing called a negative distance between the two atoms. So, the two atoms can be far away where the distance is very large, the positive and very large, there is the distance is 10 millimeter or 10 micrometer or 10 nanometer, and then they can come closer and closer, nanometer, micrometer, nanometer range and angstrom range, and they can come maximum 0 distance. There is nothing called negative distance. So, we would not discuss the negative part, we will only discuss, we are only interested in the positive part. So, the x starts from 0 and goes to positive, and we want to see how does this function look like in this part. So, x is 0 or x is greater than 0, greater than or equal to 0. So, we are interested only in x is greater than or equal to 0. So, now in that sense, in this recipe, f of minus infinity has no meaning, because x does not go to infinity, it is not a physical thing for us. So, we will evaluate the function at f equal to infinity and f equal to 0. So, have a look at this function, have a look at x equal to infinity, 1 over infinity is 0, here is also infinity is the denominator. So, 1 over infinity is 0, at x equal to infinity this function will go to 0. So, as the x goes to very large, the function should reach 0. So, this is 0 and this is positive, okay, and this is also positive. So, this is the origin 0 point. So, as x goes very large, our aim is that the function should reach 0. That is the first recipe. The second recipe is find out the point where f of x equal to 0. So, the next point is to find out where this function is 0. So, let us quickly do this, the recipe, the protocol, the number 2, which is find out where a by x power 12 minus b by x power 6 equal to 0. This implies, what does this imply? This means that a by x power 12 equal to b by x power 6. This implies that x power 12, x power 6 by x power 12 is equal to, I can take this way, b by a. So, let us do it slowly, So, what does this imply? This implies I can take x power 12 this side and x power 6 this side. So, sorry, x power 12 this side and b this side. So, I can say a by b is equal to x power 12 by x power 6. So, this implies that a by b is x power 6. So, that this essentially leads to the value which is when x is equal to a by b whole power 1 by 6, when x is equal to a by b whole power 1 by 6, f of x is 0. So, this is the value where f of x equal to 0. Now, the next recipe thing says that find out the where it has a maximum or a minimum. So, just before that we forgot one thing, we wanted to find out the function at x equal to 0. So, f at x equal to 0 is a by 0 minus b by 0, which is basically infinity. So, at x equal to 0 the function is infinity. So, that we know. Now, we want to find out the derivative. So, what is the derivative of this function? So, we want to find out the derivative of this function, which is df by dx is d by dx of a by x power 12 minus b by x power 6. So, I will quickly do this. So, x bar you can, so basically the derivative of this is a into minus 12 x power minus 13 minus b by this is plus 6 x power minus 7. So, this is the derivative and df by dx equal to 0 implies, so we want to find out the derivative and equate it to 0. So, this equal to 0. So, this equal to 0 implies again, what does this imply? This implies that x power minus, so we can take all this side. So, x power minus 13 divided by x power minus 7 is equal to 12 a by, so you should do this carefully. So, one should, what do you want? Let us do it carefully a little more. So, what we want is df by dx equal to 0. So, let us equate this to 0. So, what we want is, let us have a look at it. So, we want minus 12 a by x power 13 equal to minus 6 b by x power 7. This is what it means. So, this means that I can, this is divide this and there are 2 and this says that 2 a by b is equal to x power 6. So, x is equal to 2 a by b square root of the 6 1 by 6, or this means 2 a by b whole power 1 by 6. So, at this particular value, when x is 2 a by b whole power 1 by 6, the derivative is 0. Now, you substitute this now you want to find out the second derivative. So, what you should do is that find the second derivative and substitute it, and you will see that it is a minima, it is a minimum at this particular value. So, at this value of 2 a by b whole power 1 by 6, it is a minimum. So, we learned a few things. We learned that at x equal to 0 is infinity. So, the function should go to infinity. At x equal to infinity, it should go to 0, and there is a minimum somewhere here. And we also will learn that it crosses 0 here. So, there is a point where it crosses 0. So, if you use all this information and combine this, what you will find that it crosses 0, there is a minimum here, and it should go to 0 like this. So, you will get something like this as f of x versus x. So, this will be a by x power 12 minus b by x power 6. So, I am doing it in a hurry because we have today in this lecture, I already described your protocol and an example, and I quickly wanted to tell you that if you use this example, use this in an assignment or use it as a take home question and do this plotting yourself, and you will find a plot which look like this. I already explained to you this is 0, this is infinity, there is a minimum here, and it crosses 0 at one point. So, all this is clear to you. So, this is the thing which the answer will look like this. So, do it yourself. So, what the to summarize what we learned is we first briefly discussed some applications by pulling DNA, unzipping of DNA, and the force is basically derivative of free energy and distance. Force and distance are derivatives of free energy, and dg by df is distance. Then we discussed a protocol, a recipe to sketch functions by calculating where is the maximum, where is the minimum, where are the minima and maxima, and where are the zeros of the function at plus or minus infinities, whether it will go to infinity or what will be the value of the function. And knowing a few things and combining this knowledge, we can roughly sketch the behavior of the function. So, we learned this much. You should do many such examples yourself, have a look at the textbook offered in the syllabus, and you should learn this to plot many more functions. So, in this lecture we will stop here. In the next lecture we will continue with more on different things in calculus. So, at this moment we stop here. Thank you.